scrap paper in philosophy 17. This is a continuation from last video, and uh, we were looking at this formula for mass. We are doing a retreat into physics, and just to be true to this formula, because we're going to eventually have to use it in the context of special relativity to get anywhere with this issue about the speed of light. So before we do that, we have to realize that in the case of no force being applied, this formula gave an indeterminate force, an indeterminate form, because the numerator is zero, the denominator is zero, so is the numerator. And so we're going to have the great idea of multiplying both sides of this equation by this difference in velocity, v1 minus v naught. And when we do that, we get mass times v1 minus v naught equals force. And then you can see that this expression cancels, and it equals force times time. So we associate zero force with a zero change in momentum, because by pattern matching we create this quantity mass times velocity, which equals momentum. And since velocity is a vector, so is momentum. Again, we were doing one dimension last time, and I was giving you a toy universe in one dimension to show you how we can think about the luminocentric principle in physical terms, but eventually we're going to have to wean ourselves away from one dimension. So we have this expression, momentum is the mass times the velocity, where I circled this expression here. Momentum is a vector, and so is velocity, and mass is a scalar. And so we have, I wrote down here what the velocity equals in terms of a vector, but I replaced the XYZ coordinates, which are space, by the rate of change of these coordinates in time, which is then the velocity vector. And just to remind ourselves of what the expression for the norm of velocity actually looks like, it's the square root of this sum of squares. In 3 dimensions, which eventually we're going to need. And just to continue, just to wrap this up, we have force equals the rate of change with respect to time of momentum. Why are we doing this? Well, because it's the traditional understanding of these quantities. So I guess, did we get rid of the indeterminate form for the mass? Well, the mass, here's what this expression, this derivative of momentum with respect to time equals. It's the mass times the acceleration vector, which is what I wrote down here, the second derivatives of the position xyz with respect to time. And so now I put an arrow on top of f to realize that we're in a vector world now, where force is a vector, and it equals the mass. which again, it's the law of conservation of mass. It somehow has an independent existence times this vector, which is the acceleration vector. And what we are implying is that x with this kind of formulation is that xyz is the position of mass m, which is a position that is changing in time because mass m is changing its position in time. And when we write the Schrodinger wave equation and solve it, this probability, what we get instead of xyz is the probability that xyz is the position of the mass. And if I wanted to be really, really strict about this, I would have to write x naught, y naught, and z naught here instead of just x, y, and z. But the point is that if we evaluate this, the integral of the complex conjugate of the expressions for the waves at the given coordinates, x, y, z, from little change delta d in that we're subtracting from the coordinates all the way to a change of positive delta d, which we are adding to the coordinates, and we integrate this, then we should get a probability of finding a mass there on those coordinates. We have seen that we have completely lost the coordinates of mass, but we have a sextuple, which is x, y, z, t, the real part of the wave, or the wave, which I wrote down here, which is, of course, is really two quantities, the real part of the wave on these coordinates and the imaginary part of the wave on these coordinates, because the wave is a complex valued function. And the reason why this wraps up the discussion is that we sort of know what to look for now. We have to look for how the Schrodinger wave equation is, if the Schrodinger wave equation really is somehow playing this game here, which I boxed in here. Is this really the game that's being played by the Schrodinger equation? So that's one thing I'm going to look at. But this expression here is, if we wanted to give it a name, we would call the conversion, the equations for a full conversion from mass to energy. If you're converting mass to energy completely, what you expect is that the norm of the velocity of the difference between the original speed of the mass and the final speed of the mass is going to be c, and the difference between the velocity of this energy, which is stationary, and this mass, which was not stationary, is going to be equal to negative c, and that somehow got to show up somewhere. If you multiply c by I, and then you multiply that quantity by I again, you're going to get I squared. That's a negative number. But we're going to try to think about this in a very careful sense, because we haven't adjudicated the circular motion yet, which seems very important, because what I'm trying to get at is the spinning magnet hypothesis for the electromagnetic wave, which would put the circular motion in a very important in a very in a prime, as a prime example of being stationary. I mean, you spin so you spin so fast that you don't that you're spinning in place, which is this idea of being stationary in vacuum. If you can spin fast enough, you're going to be spinning in place. And so there's more that I have to think about before I can tell you if this is really going anywhere. But the luminocentric principle to me is very clear, because this corollary of special relativity, if we measure our speed with respect to electromagnetic waves in vacuum, the result equals c, no matter what direction they're moving. And even if the two waves are moving completely apart from each other, we would expect 2c, but instead we measure c. And the coordinate postulate is just, I mean, the coordinate postulate is just logical reasoning, because we haven't settled yet on the speed of light, on the speed of electromagnetic waves, if it's 0 or if it's equal to c. I mean, if we want to play the special relativity game where both are equally valid, well, then it turns out that one of them breaks the symmetry, because it has the same speed in every direction. That one has to break the symmetry. That one has to be 0. Thank you.